For subtopic number 3, which is on electric potential. So you have to be able to define what is electric potential, define and sketch equipotential lines and surfaces of isolated charge and a uniform electric field. Use this equation for a point charge in a system of charges in 2 dimensions. Apply potential difference between 2 points. Apply the change in potential energy between 2 points in electric field. And lastly, apply potential energy of a system of point charges maximum up to 3 charge. Okay. So electric potential symbol dia adalah V. So it is defined as the work done by external force per unit charge to bring a test charge, which is a positive charge, from infinity to a point in an electric field, produced by a source point charge, which is Q lah, capital Q. Oh, it's capital Q. Tapi saya tulis Q di sini. Sorry. That's okay there. That's okay, right? Yeah. So this is the test charge, this is the point charge. So it is the work done to bring this test charge from infinity to a point in an electric field produced by this point charge here. Okay, so that is electric potential. It is a scalar quantity with the SI unit of joule per coulomb ataupun volt. So it can be calculated using this equation here, where K is the Coulomb's constant, Q is the point charge, include the sign of charge in calculation, okay? So for electric potential, kamu perlu include lah, kalau dia negative, kamu perlu letak negative. And then R, which is the distance from the point charge to a point at which the potential is evaluated lah. Alright, so equipotential lines and surfaces. So this are where all points have the same potential lah, okay? So they have the same potential. And each equipotential lines has its own electric potential. So if you look at an isolated charge, this is the equipotential lines, which each of this has its own electric potential lah. So this is 2 volt, 5 volt, then makin dekat dengan the charge, makin besar lah the value. Makin jauh, makin kecil. Untuk uniform electric field pula, these are the equipotential lines. This is what it meant when the electric field lines fringe apart near the edges. Okay, so instead of just parallel like this, it fringe a little bit at the edges. Okay. Right, so the important properties of equipotential surfaces are, so equipotential surfaces are this one here and this one. So the electric field at every point on an equipotential surface will be perpendicular to the surface, okay? And then the electric potential points in the direction of decreasing electric potential, okay? So this is the electric field kan, so it points towards a decrease in electric potential, okay? Sama je macam ni, from 100 volt to 0 volt, so dia decreasing lah, maksudnya dia point towards a decreasing of electric potential punya value. So the surfaces are closer together where the electric field is stronger, and further apart where the electric field is weaker. No two equipotential surfaces can intersect each other. Kalau they intersect tu maksudnya at the point of intersection they have two directions of electric field, which does not make sense. Okay, so they cannot intersect with each other. Okay, so the electric potential difference between 2 points can be calculated using this equation here. So the potential difference between points B and A in an electric field is defined as the work done in bringing a positive point charge from point A to point B in an electric field per unit charge, okay? So it is the work done in bringing this charge here from this point to this point here, okay? So the formula is given here, where delta VBA is V final minus V initial, which is basically just VB minus VA lah. Okay, so the potential difference between any points on an equipotential surface is 0. Okay, so there is no work required to move a charge at constant speed along an equipotential surface. Okay, so maksudnya sekarang ni satu equipotential lines, kalau dia mau move from point A to point C, the work done is equal to 0 because they are at the same equipotential. Okay, similarly as from point F to point E, work pun 0, but from point A to point B, there is a value. It is not equal to 0. Okay. Okay, so delta V is okay lah. So basically the electric potential, since they are in the same equipotential lines, electric potential at point A, point C, and point D is equal. Similarly as point B, point F, and point E. Okay, so they will have the same electric potential. Okay, so let's look at example number 4. A point charge Q1, which is this one here, is at the origin, and a point charge Q2, negative 2 microcoulomb, is on the x-axis at the coordinate of 30 meter. So we have to find the total electric potential due to these charges at point P here. Okay, so this is just a scalar quantity. So we just have to find the magnitude of electric potential. So V1 is equal to K Q1 R1. Okay, so this is 9 times 10 to the power of 9. Q1 is equal to 5 micro. And then the distance is, so this is at a coordinate of 0, 4. So this is x, this is y. So maksudnya the distance here is equal to 4 lah. So this is 4, which gives you 11250 volt. Untuk V2 pula, this is K Q2 over R2. So this is 9. This is negative 2. Okay, remember you have to include the negative sign lah untuk electric potential sahaja. Over the distance, so this is 3, this is 4, so this will be 5 lah based on trigonometry. So this is 5, which gives you negative 4500 volt. So since this is just a scalar quantity, we will just be adding these two together lah. So V1 plus V2. So this is minus, which gives you 6750 volt. Okay, so this is the electric potential at point P. Okay, so that's on example number 4. Next, if we were to ask about the change in potential energy, we will then be looking at the work done, right? So to find the work done to move a charge, the equation for change in potential difference can be written as the one shown here. Okay, so the work is done either by electric force ataupun by an external force when a charged particle moves in an electric field region lah. So if W is positive, the work is done by external force. Positive external force. The potential energy will increase. If the work done is negative, it is done by an electric force. It is done by the electric force, and the potential energy will decrease. If the electric potential at a point in an electric field is V, then the test charge Q located at that point will have an electric potential energy of UQV. Okay, so this is the equation for electric potential energy. Oh, sorry, change in potential energy. So it's actually should have been, I think I'm gonna add this one because they mean that change, not just potential energy. Okay, I'm just gonna edit that later in our notes. But it's basically that equation supposed to be that way lah. Okay. where delta U is equal to U final minus U initial, V final minus V initial. Yeah. So basically this is also equal to work lah. Sebab if you look at this, Q delta V, this is also Q delta V. So this is delta U, which is also equal to work. Alright. Alright, so this diagram is just telling us the sign convention lah. Okay, so if a positive charge moves from A to B here, work is done by the electric field, which is this one here. So delta V, the change in potential difference, will be negative. Work done will also be negative since it is done by the electric field. It's electric field. Delta U will decrease, will be negative, meaning that the potential energy is decreasing lah. Okay. Similarly for this one, for this is positive charge je lah. Why is it all pointing downwards? It's because positive charge will be attracted to the negative plates lah. So delta V here will be positive, work will be positive since this is work done by an external force. Delta U will be positive and the potential is increasing. Okay, so just read through. This is the explanation. This is just the direction. Okay, next, the electric potential energy of 2-point charge. Tadi tu change in potential energy. Sekarang ni kita tengok electric potential energy of 2-point charge. So sekarang ni kita ada a system of 2 charges. The total electric potential energy can be expressed as the one shown here. Okay, so this is the meaning of each lah. So Q, the charge, you have to include dia punya sign juga lah untuk change in, untuk electric potential energy. So electric potential energy of a system of point charges, if we have 3-point charge as shown here, the total electric potential energy can be expressed as the one shown here. Okay, so let's try to apply this into this example number 5. Remember, the sign of the charge must be included for the calculation lah. Okay, so untuk this one here, I'll let this be Q1, Q2, Q3. Okay, so this is gonna be, since the distance is the same, so we can extract K over R. So we are only left with Q1, Q2, Q1, Q3 plus Q3. Okay, so this is over D. So this is gonna be Q1 is 4Q. Okay, Q2 is negative 2Q plus 4Q. Q3 is 5Q. Q2 is negative 2Q, 5Q. Okay, so calculate that. You will get 2Q squared. Okay, so from here, we just have to substitute lah the values. 9, 2 times 150 nano. Wait, I don't like how this looks. Okay, squared, yeah. D is equal to 14 centimeter. Okay, so if you were to calculate this, you will then get 2.9 times 10 to the power of negative 3 joule. All right. Okay, so that's quite straightforward actually. And that is basically our third subtopic. Okay, so our third subtopic is I would say quite confusing, not as straightforward as our first and second subtopic, but in this case what we need to know is we need to be able to use this equation here, and we have to include the sign of the charge, and then we have work which is equal to Q delta V. We also have delta U which is equal to Q delta V, and then we have electric potential energy which is K Q1 Q2 over R12. Again, all of this have to include sign lah untuk electric potential. And we have for 3-point charge to juga. That's a bit long for me to rewrite it, but just make sure you know how to use all of these equations lah. Okay. All right, so that is on electric potential and on our third subtopic.